Presentation by Ian Walker. Thank you for staying. If you're just joining us now, Ian Walker, Senior Applications Engineer at GMW, gave a presentation on coreless, clip-on, and clamp-on current probes for test stand and in-vehicle current monitoring. These presentations are being recorded, and my understanding is the recording will be made available to you, so I encourage you to go back and watch his. If you can also just reach out, leave us a message, and I'll make sure a copy gets sent to you. My name is Ben Hartzell. I'm Vice President of Marketing at GMW, and I've been with GMW for 10 years. We're going to save time for questions and answers at the end, so please, just in the Q&A chat box, type any questions you have. Ian Walker is also still here with us, so if you had any questions about his presentation and you'd like to ask him, we can go ahead and answer those at that time as well. Now let's get started. Today, I'm going to be talking about current measurement for electric vehicle charger tests. This is going to be just a broad overview of various different types of current probes, an overview of where those current measurement points might be in an electric vehicle charging system, a summary of the current sensor types, basic operating principle type, and the advantages for certain measurements points. Why would you use a specific probe at a certain spot? Here we have a simplified diagram of the charging system on an electric vehicle. The current probe connections of interest are in blue and in red, as indicated. The blue probes are indicating measuring individual cables, bus bars, or other conductors. The red probes indicate measuring the total current of all conductors at that point in the system. For example, all three phases of three-phase power, or both the positive and negative conductors leading to and from the main battery. The red probes are measuring the sum of all currents enclosed and should result in a measurement of zero if there is no leakage or loss. If there is an unexpected non-zero measurement, then we have some sort of loss we need to troubleshoot. All the probes we're talking about today are analog probes with either a voltage signal equal to the sensitivity times the primary current, or a secondary current output signal equal to the primary current divided by the number of turns. I'll get into the details of both types later. Well, stepping through this diagram, starting here at the top left, we have in-vehicle chargers. Here we're talking about either level 1 AC charging, typically 1 kilowatt or so, and level 2 AC charging all the way up to 12 kilowatts, either single phase or three-phase AC mains power. The measurement points here are the individual conductors to measure the current coming from the AC mains, or all conductors coming from AC mains to measure, to look for leakage. From there, we have an AC to DC inverter, and we have another measurement point on the DC output of the inverter. And assuming that we are in a charging stage, we have another DC to DC inverter with measurement points again on the input and the output of the inverter. On the lower half of the diagram here, we're talking about external chargers, external to the vehicle. Again, three-phase AC mains power, but we are at much higher power levels than the level 1 or 2. We're talking up to 500 kilowatts in some cases. Again, measurement points on the individual conductors. You can also measure a sum of all the conductors. Again, if you're looking for a differential measurement for leakage loss, AC to DC inverter. And then we have the high-powered DC lines there to go charge the power, charging the battery. The bottom here of the lower half is again similar input, but instead of AC to DC, we're talking AC to 85 kilohertz. And this would be for 85 kilohertz inductive charging. And here we would be measuring both the inductive transmit coil and the inductive receiving coil. And then again, after the 85 kilohertz DC inversion, we have some measurement points there. The first type of current probe I'm going to talk about today are PEM Rogowski coils. PEM is the manufacturer, and these are flexible clip-around AC current probes with an analog integrator. A Rogowski coil is an evenly wound coil with a known number of turns and a constant cross-section. The end terminal is then passed back through the center of the coil so that both end terminals end up coming out on the outside of the same end of the coil. What this means is if you have a Rogowski coil made of flexible material, you can open and close it. You don't need any electrical join in the joint. It all passes back through the same coil. We have our primary current here labeled I with an alternating current or a pulse. The Rogowski coil is sensitive to the magnetic field, and the changing current induces a voltage in the terminals here of the coil, here referred to as E. If the coil has a constant cross-section and evenly spaced number of turns, the induced voltage is proportional to the rate of change of the primary current, di dt. And here we have a very simple plot of the induced voltage. After analog integration, we have the sensitivity times I, the primary current, gives us a voltage output waveform proportional to the current waveform. As DC current has no rate of change, DC current does not induce a voltage in the coil. Rogowski coils are completely insensitive to DC. Here we're going to look briefly at the specifications of PEM Rogowski coils. You can see current ranges anywhere from 30 amps to 300 kiloamps, frequency ranges of 0.03 hertz all the way up to 50 megahertz. It's a specific ranges depending on the model. An amplitude accuracy of about 1%, and the position of the primary conductor within the cable, it only has a slight effect on the amplitude accuracy. It doesn't have to be centered, just generally farthest away from the join, but otherwise the position doesn't particularly matter. Phase shift 1 degree at the mid-range of the frequency response, very low insertion impedance, a wide operating temperature, and not here in the specs is the wide ranges of physical sizes. You saw the small one. This is a mini coil, which the mini ones can be as small as 80 millimeters and 1.7 cross section, but you can have coils all the way up to several meters long. The PEM Rogowski coils are suited at almost any AC measurement point. I've highlighted the ones here on our diagram. I've also highlighted a couple of other points. Here you see the inverter is highlighted because the smaller Rogowski coils, that 80 millimeters and 1.7 millimeter cross section, can be used to measure the power electronics there small enough, the onboard power electronics in the inverter. Another place that I've highlighted, which you may not expect actually, is the battery, the DC battery mains. And here we're taking advantage of the fact that it's insensitive to DC. Here we're looking for a ripple current, either intentional or unintentional, on top of the DC current. And the DC will be completely ignored. The Rogowski coil will only measure the AC current. Here's a specific example of a specific type, a CWT Mini 50 HF. It's on the smaller side. This is the one I've been showing you, but it's not the smallest one available. It's a little bit wider cross section, 3.5 millimeters. That's because it includes a screen to shield the Rogowski coil from capacitive coupling of high dV/dt. If we look at our first scope trace here, there's a voltage trace and two current traces. The voltage trace here, you can see, I'm tracing it out, is about 500 volts difference there, over a 12 nanosecond rise time, which calculates out to 40 volts per nanosecond. The current traces, the first one is a shunt, and the second one is a CWT 50 mini HF for comparison. And that 40 volts per nanosecond rise, there's essentially no artifact of capacitive coupling because of that high dV/dt. The second plot, it's unrelated to the first. It's a just damped sinusoidal wave. Here we're showing, again, a shunt compared to the CWT Mini 50 HF. We're showing the very accurate reproduction of the waveform and the very predictable delay. Here we have the same measurement points again. It's almost the same as the previous. The main thing here is the coil is just generally too small for these common mode differential measurements. So I've removed the highlighting here from the red coils, so the red measurement points. PEM Rogowski coils can be tailored to specific frequencies. So we're attenuating the frequencies outside our area of interest. I have two types of examples shown here. The first is a CMC common mode current AC probe. Looking here at the specs, you can see that the current range is fairly moderate, 40 to 150 amps, with a lower frequency cutoff of 2 kilohertz up to 20 kilohertz, and a high frequency cutoff of 11 megahertz to 15 megahertz. Here you can see on the plot, it is very linear until that roll-off cutoff point. And you can see here where it would be used most likely is doing the common mode current here between the motor drive and the motor. Here we have three-phase current from the drive to the motor. The frequencies can be near DC, particularly for an electric vehicle, and the differential current of all three should be zero. The CMC lower frequency cutoff, the 2 to 20 kilohertz range, is enough to attenuate the fundamental drive current. However, if there are high voltage switching here in the drive, it may induce high frequency currents, which we want to measure. These high frequency currents could then reach through the motor bearings and lubricant to ground, ultimately breaking down the lubricant. The second type of PEM current probe with tailored frequency is a probe that's optimized for 85 kilohertz. And as you probably know, the 85 kilohertz is the inductive charging frequency. And so we're optimizing a probe for higher signal to noise at that 85 kilohertz. And the lower cutoff of 50 hertz or so, insensitive to near DC currents. Getting rid of these lower frequencies helps improve the signal to noise. There's usually a little bit of low frequency noise, which it helps just if we can get rid of that. And then the probe is further optimized for 85 kilohertz with improved amplitude accuracy and good phase accuracy, both of which are critical if we're looking for power transfer measurements, measuring both the transmitting coil and the receiving coil, looking for the efficiency of power transfer. Next, I want to look at the Danisense Zero-flux Fluxgate current transducers. These are DC and AC current probes. And zero-flux current transducers, as the name implies, operates on the principle of keeping the flux within the magnetic core at zero, using a Fluxgate as the magnetic field sensor. The current transducer is a closed-loop transducer. The primary current I, flowing through a conductor, will generate a magnetic field, which then induces magnetic flux within the core. The flux is sensed by the flux sensor, which provides feedback to a compensation coil, secondary compensation coil, which has n number of turns, typically 200 to 5,000 turns. There's a small secondary current based on the feedback from the flux sensor times the number of turns to give a compensating magnetic flux in the core, which ultimately should result in zero total flux within the magnetic core. At DC and low frequency, the flux sensor consists of a flux gate, while at higher frequencies, it's instead a feedback winding to provide the feedback for the secondary current. In either case, the magnetic flux is being measured at sub-ppm levels. In the secondary compensation circuit, the current of the secondary current is measured with a burden resistor, with the voltage output equal to the compensation current times the burden resistance. This burden resistor can either be integrated in the transducer measurement head, or the burden resistor, you can then take the current signal all the way back to your measurement instrument and use the burden resistor at the instrument to get the voltage measurement there instead. Following the equations here on the right, if there is zero flux in the magnetic toroid, which is what we expect, the secondary current is equal to the primary current divided by the number of turns, again, typically 200 to 5,000. If there is no current lost in the current transducer, so no current lost in the core because of very good magnetic core materials, and no current lost here to the no power, I'm sorry, lost to the secondary compensation coil, then the insertion impedance should be roughly equal to the burden resistance over the number of turns squared. If we assume a burden resistor of 1 ohm, number of turns about 1,000, then the insertion impedance of 1 micro ohm. And the next stage of that is, okay, 1 micro ohm insertion impedance, if we have 1,000 amps primary current, again, 1,000 turns, the power lost is 1 watt. And by power lost, this is the power taken out of the primary current in order to make this measurement. Compare this to a standard 50 millivolt shunt, which at 1,000 amps would have a loss of approximately 50 watts. Danisense current transducers come in a wide variety of ranges and packages. In terms of measurement range, we start as low as 12.5 amps full scale. This is for a programmable PC map version, the DP series, all the way up to over 10,000 amps for the DR series. Outputs can be either current or voltage. Again, that's just whether the burden resistor is built into the transducer head or you're taking the signal out as the secondary current directly. And then the transducers with the burden resistor built into the transducer head are all the ones of 2000 amps or lower. The larger ones have a separate electronics box. So a rack mount electronics, and the measurement is taken out of there instead. And there is also a DSSIU, which is the system interface unit. It's a 4 or 6 channel rack mount unit, which handles all your power supplies for all your transducer heads, as well as helps organize all the signal cables. And then also there's an unpackaged version of transducers available for OEM applications. Here we're going to look at a few brief specs of 2 specific models. The first one I'm going to look at here is a DS200ID. That's the one here I have here. This transducer is a 500 turns ratio transducer, peak field of up to 370 amps. You can see very low zero offset, very good zero offset stability, very good rejection of external magnetic fields, very low amplitude error, very low phase error. The second one I'm going to mention here is a DS200ID-CD3000. It's a higher current range transducer. You can see 1500 amps peak. But it has the addition of a calibration winding of 3000 turns. So this is an additional winding around the core of the transducer, allowing an in situ calibration check of the transducer. If the calibration winding is injected with 500 milliamps multiplied by the 3000 turns of the calibration winding, we end up with 1500 ampere turns. That's the same as the full scale of this transducer. So by just doing a very low signal, we can simulate a full scale primary current. Here again, emphasizing the very good amplitude and phase. In addition to being very low, you can also see that it is very level and flat up to about 10,000 kilohertz. And even above 10,000 kilohertz, there's no resonant behavior in the amplitude or phase response at higher frequencies. So if you're doing, you need high accuracy measurements, this is a just very, very good choice. And the reason you might want high accuracy measurements is particularly for power efficiency measurements. So if you look here again in our diagram, I've measured all the, highlighted the AC and DC points, but I've also added voltage connection points, which we're not covering voltage measurements here today, but for good quality power measurements, you need both a good quality current measurement as well as voltage to calculate total power. And we're not just, you need good current phase response in addition, not just amplitude response. You need both amplitude and phase for good quality power efficiency measurements. Next, we have the Bergoz IPCT. The Bergoz IPCT is very similar to Danisense in operating principle. It's also a DC-AC zero-flux Fluxgate current transducer, but there are several different key differences in the specifications. It's very high resolution. You can see here 30 microamps on a 2-amp full scale. So you can also see that the scale is much lower than the Danisense was, but very high resolution. And it has a very large aperture. So given that you might be measuring 2 amps, it has an 83 aperture over 3 inches, which is large enough to pass a very large cable bundle through. Here I have actually just a 3-phase charging cable. You can see clears through no problem. And you can see here on our drawing, we've shown 3-phase I1, I2, and I3, so 3-phase power passing through. And so this is going to measure the total current of all 3 phases. So I total is I1 plus I2 plus I3. We then get a voltage signal output equal to the sensitivity times I total, again, all 3 phases. And so if there is some sort of leakage or loss, this very high resolution will allow us to see it, the very low noise. And another feature here that may be useful is the recovery after overload. So 1,000 times overload current, it will recover very quickly, less than 10 milliseconds. We also have a newer version here, the LP-IPCT, which is smaller, more compact, and lighter, but the aperture is also smaller. So depending on where you tend to use it, it may be a little bit more difficult to get these large cable bundles through. But the main advantage here is the higher resolution. And so here you see the connection points. They're going to be anywhere we would want to make that differential measurement in order to look for any sort of leakage or loss. So any multi-phase measurement, or again, the positive and negative here on the battery for the DC battery charging currents. The last current measurement instrument I'm going to cover today is the GMW CPC and a little bit on the GMW CPCO clip-on current probes. Ian's presentation earlier today was solely on this topic, so if you want to learn more depth than I'm showing today, I encourage you to go look at his presentation. But here I will do a brief overview. All of the prior probes we've discussed form a continuous loop around the conductor being measured, whether it's a continuous coil, as with the Rogowski coil, or with a solid magnetic toroid core, as with the Danisense and Bergoz current transducers. Ampere's circuital law, in short, says the magnetic field induced by the current flowing through the conductor can be calculated with the line integral of the magnetic field around some closed curve. The curve can be of any shape, it just needs to be continuous and closed. And the law will inherently says that any external fields will inherently be rejected. The CPC clip-on current probe and the related CPCO clamp-on current probe are designed with the idea that Ampere's law, a circuital law, can be approximated with many individual magnetic sensors along a curve outside the conductor, and rather than integrating the continuous curve, we do a summation of the magnetic field at these points around the curve instead. This, in combination with several other tricks, gives an approximate but still quite good measurement of the current within the curve while rejecting magnetic fields and currents outside the curve. Again, for more detail on the operating principle, please see Ian Walker's presentation. By having no magnetic core, the CPC current probe very light, compact, thin cross section. The small size and clip-on form factor make it very easy to install in awkward locations. The lightweight is more than just convenient, however. It also is useful in vibrating environments. It's easy to secure. Well, you can't really see against the background, but I have a couple of cable ties. Easy to secure with, say, cable tie compared to having to mount a heavier measurement device. The package is sealed, moisture resistant, temperature range minus 40 degrees Celsius to 100 degrees Celsius, suitable for harsh environments. These are commonly used in test cell chambers with moisture and large temperature cycles with repeat frost and thaw cycles. Another example of a harsh environment here is shown here in the picture. This is the larger related CPCO, which is based on the same principle and same technology, but it's larger, 77 millimeter aperture or 160 millimeter versus the 27 of the CPC. In this picture here, the CPCO is being used in an electrical chemical plant, which is a pretty harsh environment and used without problem for several months. Another example of a harsh environment where CPCs and CPCOs are commonly used, we see them at transit agencies measuring high voltage lines, high current conductors for bus or light rail, either as a quick diagnostics or as a long-term redundant monitoring. The CPC and CPCO both have pretty high ranges, starting at 250 amps for the CPC, up to models at 2,000 amps. The CPCO has models up to 16 kiloamps. Frequency range DC to 75 kilohertz. Amplitude error less than 1%. High rejection of external magnetic fields. Fast response time 2 microseconds. Low insertion impedance. And again, I've mentioned the environmental qualities of it. One thing that's also good to mention here, though, is the power supply. About 5 volts, less than 85 milliamps, which is the same as a USB port spec. So you could run this off the USB port on your measurement device, your scope or data logger. You could offer the power from an external power supply, or you could use an external USB battery pack. So the CPC probe is good pretty much anywhere for quick diagnostics and long-term monitoring on almost any single conductor within the charging system. It's easy to open the jaws, compact size, lightweight, make it easy to install around existing cables and bus bars. Just a quick example of that. You can see it's very easy to just clip, thread around the one cable of interest, which is actually some of the advantages you saw of the PEM Rogowski coil earlier. I can only do it with two hands, so I'm just going to slide it on. But you can imagine that this Rogowski coil was very easy to open and close around an individual conductor, very lightweight, easy to thread through in tight spaces. Very similar benefits to the CPC, except you're getting a DC-AC probe rather than an AC-only probe of the Rogowski coil. Another example use for in-vehicle test could be if you're doing a road test. The lightweight probe can be mounted wherever you need to make a measurement point within the vehicle with a single cable for power and signal running to your portable data log elsewhere within the vehicle. There's one more instrument I want to talk about today, but it's not a current probe. We're actually going to mention magnetic field transducer here. It's a 3-component AC magnetic field transducer. The Senis 3DA CMT is 3 components, AC magnetic field transducer. What that means is we're measuring both BX, BY, and BZ, all 3 vector components of the magnetic field within this same sensitive volume of 10 by 10 by 10 millimeters. For each BX, BY, and BZ, you have a separate output of VX, BY, BZ. That's a voltage proportional to the field. The small physical size, the small sensitive volume are useful for measuring the field between and around inductive charging coils. Now, while the field between the charging coils might be easy to model, still useful to be able to verify your model with a measurement. But what would be more tricky to model would be the environment. What other ferromagnetic materials you have in the environment around it. And so here, being able to have both the small physical size as well as the high field resolution, you can make a good map of the fringe field and how the field distorts and interacts with the environment around your charging coils. The Senis 3DA CMT is optimized for 85 kilohertz with a frequency range of lower end about 10 kilohertz up to 200 kilohertz, field range of plus or minus 10 millitesla, and again, that high field resolution, 1.5 microtesla RMS. So here, the obvious measurement point, of course, is your 85 kilohertz charging. You have both the transmit and receive coils as well as the fringe field around them. We have a little bit of time for questions, so thank you. Please type in any questions you have. Again, my name is Ben Hartzell. I've got my contact information there. Ian Walker is also still here in the room with me, so if you have any questions for him, please. And we'll just wait a few minutes to see if anyone has questions.